thanks all for coming, also to the online participants. I hope all of this is working well. So for those of you who don't know me very well, I have also studied, for example, in London sometime with Christian. I visited Chidem in Istanbul for some time. I spent some time in Japan. So I really think that this international exchange, going abroad, really shapes your character and brings new ideas. So I think it's really cool that we can also bring the world to KIT with these programs. So with that, I would already transition to our first speaker. So Professor Christian Beck from Queen Mary University of London. As I said, I did my Marie Curie fellowship with him 2019 till 21. Christian is well known in the statistical physics community. He was the chairman for the nonlinear physics and statistical mechanics board at the European Physical Society for quite some years. He was an Alan Turing fellow, so one of the renowned data science institutes in London. And without much further ado, I would hand the word to Christian and his talk, let's see, on data-driven load profiles, which is also based on some joint work. So Christian, please.
Thank you very much, Elena and Benjamin, for this very kind introduction. I must say it's a great pleasure for me to be here at KIT in Karlsruhe, and congratulations to your Excellence Fellowship Program. I think it's a great idea. I will suggest it to the University of London to do something similar. It's fantastic to be here, and I must say I enjoy very much my research stay here at the AIA and in particular in the Dracos group, and it's a great pleasure to be here. And now I've had to decide what I want to talk about, and I've chosen one of many topics I've been working on. It's on data-driven load profiles and the complex dynamics of electricity consumption. You will, after this talk, probably know why I should add the word complex there. It's really something very complicated from a mathematical and statistical point of view, and it actually yields quite interesting material for people like me who work in complex systems research in general. So this is a joint work with Mehmet Anvari, who's in Potsdam, and Elizabeth Prodro, I think she was in Oldenburg at that time, and Benjamin, you know, Benjamin Schäfer. It's also Holger Kranz from the Max Planck Institute in Dresden, and Mark Timmel from the Technical University of Dresden, and myself. So in this talk, I want to do a kind of non-specialist approach. I know here really fantastic experts in the field, but I want to keep the talk simple that everybody can follow. So I will give you a very basic introduction to the properties of power grids these days if they have a large fraction of renewable energy generation in them. I will talk a little bit about a statistical analysis of frequency fluctuations that occur in various types of grids. And I see here a couple of PhD students who do precisely that in much more detailed way than I can do in this talk here. And then I will come to the most interesting fluctuations of all, that are the fluctuations induced by human beings who use the electricity. And you will see it's really getting mathematically tricky at that stage. So here we go. Everybody in this room and online knows that these days we have an energy transition. There's not anymore this single big power plant that produces all the energy, and things were simple 30 years ago. Now, the energy production is much more heterogeneous. You have, let's say, some wind farm over there and some solar panels over there. And it's not anymore a big power plant, but a very heterogeneous system. And therefore, understanding the structure of this power grid with these many non-homogeneous sources and things is far from being trivial. It's pretty complicated. What is interesting is that we have an observable that we can measure, and with this observable we can see whether our theoretical models are successful. That is the frequency deviation from 50 hertz. For the non-experts, you might simply think if you plug into the socket, you just get 50 hertz out of it. But if you do very precise measurements, you see there are all the time tiny fluctuations around these 50 hertz. And they are a very informative signal because they have quite an interesting and useful physical interpretation. That is the following interpretation. If the frequency is a little bit less than 50 hertz temporary, it means there's a lot of demand by consumers in the power grid. The turbines work hard to meet the demand and more power production is actually needed. Whereas if you measure temporarily a tiny little bit more than 50 hertz, then there's less demand by consumers. There's a surplus of power and you need to get rid of the power. And therefore, this frequency variable is a fantastic experimental signal. It describes the really the difference between production and demand in the net, and therefore it's quite an interesting observable to study, first of all, experimentally, and then make theoretical models for that. From the theoretical point of view, power grid engineers have lots of models. They are of different degrees of complexity. The simplest model is really what is called the swing equation. You have there this equation where you have the frequency of 50 hertz, and the deviation from that is called theta dot in this model. And then basically, the change of this frequency deviation is just given by the feed-in of power from the system. Then there are damping terms in the system. These are control actions that are done. And there's also coupling term of the various nodes of the power grid system. And in the physics community, very often one uses these types of models where you have such as sine theta j minus theta I coupling different nodes. But much more complicated models are possible. And the coupling matrix, there's then really influenced by the topology of the power grid that you're studying. Now, why is all this interesting also from a fundamental point of view? Of course, it's also very important from a technical point of view, but to me personally, I'm quite fascinated by power grids because they are definitely the largest machines on Earth. If you ask a non-expert, let's say in the street, what do you think is the biggest machine on Earth? And maybe they say the Large Hadron Collider at CERN or something like that. But in reality, it's the power grids who span the whole of Europe or the whole of a continent often, and they are also the most complex machines because they are directly coupled to the humans who use the electricity, and these humans, as you will see, are pretty unpredictable sometimes in their behavior. So it's really interesting stuff also from a fundamental point of view to understand these largest machines on Earth. I was working, as Benjamin said, on statistical physics and dynamical systems until 2017 or so, when Benjamin, as a young PhD student, came to London for a visit and introduced me to the topic. And that left quite an impression because we started discussing and we had the idea that we could use some models from statistical physics that are well known. They are so-called super statistical models as models to describe the behavior of this frequency deviation from 50 hertz. And at that time, also a couple of new data were produced with measurement devices. I think they were produced here, these measurement devices at KIT, as far as I remember. Hello, welcome, yes. And these measurement devices yielded fantastic new data. And I show you here an example of these time series that were measured at the time. At the top, you see the frequency trajectory over 24 hours over a period of time of 1 day. And then you see the yellow line is the most likely frequency you observe over time, but then this measurement is repeated the next day, and then you see again deviations. And the gray area is the area where this frequency signal around 50 hertz is moving around. And this gives you, the gray area gives you an estimate for something that applied mathematicians and statistical physics people like me are very interested. It gives you a measure of the variance of the signal, how broad this signal is in the PDF, in the probability density function. And what one saw, and what wasn't at the beginning clear why that is so, is on a finite time scale, you see here every 15 minutes that the frequency deviation jumps a little bit. Every 15 minutes, there's a little jump, and then you get a new signal, again, fluctuations. That's what you see on the right-hand side. And also what you see here is that the gray area in the third part of the plot and in the fourth part of the plot is a bit bigger than in the second part of the plot. So the variance of the signal itself is depending on time. So the variance is really the width of the probability density function of the signal. So that is non-stationary. And we have here something that in the statistical physics community was modeled already 20 years as a so-called super statistical process. That is a stochastic process where the variance has some value right now, and then after a while it has a different variance, and then again a new variance is chosen. So these types of mathematical models appear to be reflected by these data. So therefore, at that time, Benjamin and I discussed a little bit, and the result of that discussion was then this Nature Energy paper, where we just looked at lots of data and applied super statistical modeling to it. Namely, in particular, when you do a PDF of the frequency deviation around 50 hertz, that is, you observe how often the frequency takes a particular value there, then you see here in this histogram, that is a logarithmic plot. In a logarithmic plot, a Gaussian distribution would be a parabola because you take the logarithm of a Gaussian. That would be the orange line. But what is observed is much better represented here by this blue line. And that is a particular probability density function that is called Q Gaussian in our statistical physics community. And that fits the data very well here. And there are other models, of course, for heavy-tailed distributions like this green line here that is from stable processes, but they have two heavy tails. So it's just in between stable alpha distributions and Gaussian distributions. These Q Gaussians seem to fit the data pretty well. So therefore, the idea was then, how can we concretely apply these methods from statistical physics to the modern power grid measurements? And the idea is the following, so you won't see many formulas here, don't be scared, but this is perhaps a nice one for those of you who do statistical physics a little bit or know it from their undergraduate studies. In statistical physics, you have a quantity called the Boltzmann factor. That is this factor here, e to the minus beta e. Beta is the inverse temperature, E is the energy of the system. And the probability in statistical physics to find the system in an energy state E is simply proportional to this Boltzmann factor, e to the minus beta e. Now, in non-equilibrium statistical physics, temperature is not anymore constant, but it fluctuates. And in the super statistics approach that I mentioned, you know the probability density to find a particular value of the inverse temperature beta at a certain time. So this probability density f of beta is known. And what you then do in these statistical physics models describing non-equilibrium effects, you integrate over all possible temperature states or inverse temperature states in the system, weighted with the probability to find this inverse temperature state. So this is this integral here on the left. And if you do that and choose for E the quadratic function, meaning you integrate over Gaussians that have a fluctuating variance, beta is a variance parameter here, then just if you do the integration, you end up with something that is called a Q Gaussian here on the right-hand side in these types of statistical models. It's actually a power law. It's a function that has heavy tails, that is not as rapidly decaying as a Gaussian distribution. It has heavy tails. And this integration is exact, and you get precisely that if f of beta is what is called a chi-square distribution. So it's a very common example of a distribution for random variables that take positive values. And in that way, you can explain then heavy tails that you see, for example, in the frequency data as a mixture of Gaussian processes where the variance described by the parameter beta itself is also distributed. It takes for a while this variance, then another variance, and so on. This was precisely the picture that we saw in the data there that I showed you. And from that point of view, it was then clear when Benjamin and I discussed that we need to sort of make a super statistical model for this frequency deviation. You take their locally linear Langevin equation, that's just a stochastic differential equation, very well known in the field. It is Gaussian, and then you let the parameters of that stochastic differential equation evolve in time as well. And then you can reproduce these frequency deviation statistics pretty well. So, so far so good. That was then our model, but interesting in particular for me was that all these new data came in now, and it turned out, whereas for many power grids this Q Gaussian distribution described the data very well, there were lots of differences in the correlation function, which is another quantity statistical physicists are interested in. They look at the correlation function of a signal, that is this quantity here. So they look at different times and then average over, for a given time difference delta t, average this product of the signal at different times, and that's called the correlation function. And you see this correlation function is plotted there for different power grids. You see Great Britain, you see the Nordic grid, you see Mallorca, all kinds of different power grids. And you see with this correlation function, then there are subtle differences between the different power grids, and that has to do with different spectra of renewable energy generation in these power grids. It has to do with different consumer patterns. It has to do with different control mechanisms. So apparently these tiny deviations from the frequency that you can measure are a great playground for modelers to understand why certain distributions are there and why the correlation function looks this way and not in a different way. For example, you see here also the peaks at the 15 minutes and 30 minutes and 40 minutes. This is due to trading actions for all these power grids. Every 15 minutes, a new contract is given to some energy companies to feed in power into the system. So that is interesting stuff. And we notice more and more that it's different from power grid to power grid if you go into the fine details. So apparently it was then necessary to get a database. What do all these different power grids have in common, and what is different in these different power grids? So that was, for example, this IAA access, where we looked at new data and made further mathematical models about that one. But another paper I show you in a minute. Before I come to that, I just show you this distribution f of beta, which I introduced purely mathematically because it comes from the modeling community where I work. That can be then really extracted from a measured frequency trajectory. There's an algorithm to extract that f of beta, and you can compare it with different distributions, the chi-square distribution, which I showed you so far, but other distributions often occur in the field for f of beta. That is, so to speak, the distribution of the fluctuating variance, how it's distributed. And here's a log normal distribution that gives a very good fit for the Japanese power grid. So for some reason, that Japanese power grid is perfectly described by what we call log normal superstatistics, whereas other power grids are better described by chi-square superstatistics. These are tiny differences. You don't need to worry about it if you don't dig into the mathematical details, but perhaps quite interesting. I talked about fundamental physics. This log normal superstatistics that fits the Japanese power grid very, very precisely is precisely the statistics that people observe in so-called Lagrangian turbulence. So if you have a little particle in a turbulent flow and look at the statistics of the energy dissipation and the distribution of the velocity differences of the particle, it's very similar to this, what the frequency does for Japanese power grids. Okay, so we talked about these Q Gaussians, and then you can ask questions. Are there some power grids perhaps that have heavier tails than others? That is described by the parameter Q that I introduced in the Q Gaussian. And there, kind of physical intuition comes again into play. You might conjecture that if you have a small grid, let's say for an island, the fluctuations will be higher around the 50 Hertz because there's not so many components that can average out, right? And that is precisely the question we asked at that time. Do islands perhaps have bigger fluctuations and heavier tails in the power grid dynamics than much bigger power grids? And that is true. You see here for Iceland, it's heavy tails. And I learned this from a talk by Benjamin. It's a little joke. So you see here a church in Reykjavik, and apparently they already saw this kind of heavy tails in their architecture there in a very similar way. Good. Anyway, so we then saw more and more different power grids behave differently, and it was about time to get a good database. So more and more measurements came in, and that led then to this nature communication, where a couple of people were involved that are also in this room. So, for example, Veit Hagenmeier is also taking part in that paper, and Shidem Yalcin is also on that paper. And because in that case we got data from Istanbul, and so Leo Rudin Goyao. So I would say the first and the last author of that paper did the main work as so often, and the others contributed nicely, but it's really those two who did the main part of the work, I would say. And what is interesting there is that you can then classify the different power grid data into islands, continents, and so on, and see what are differences and what are common features in these different power grids. So I think it's a very useful database that has been created there in this work. For example, you see here again what I just mentioned before. If you look at frequency deviation from the 50 Hertz, then for islands, there are much heavier tails than for continents. In this case, we looked at the frequency increments. That is also a technique that is very well known in statistical physics and turbulent theory. You don't look at the velocity of a particle itself, but at velocity differences in the turbulent flow. That's a very good technique, and that often amplifies heavy tails and gives you more information on the system. So in this paper, that was also the idea. Look at frequency differences of the deviation from 50 Hertz, and of that you take the differences on a certain time scale and then look at the PDFs of that signal. That is called increment statistics in statistic physics. It's a very useful quantity. You then have an additional parameter which tells you on which scale you measure the increment, and you see the kurtosis, which is a measure of how heavy the tails are in your distribution. That is much higher on small time scales where you measure the increment than on large time scales. Again, a phenomenon that people have described for turbulent flows before. So you might be a bit shocked that turbulent flows, which are generally regarded as being something extremely random and chaotic, that their statistics appears in these tiny power grid fluctuations around 50 Hertz. Another interesting thing that one could look at is, let's say something happens in Lisbon, there's maybe a terror attack or some failure of a big power producing point. How does such a disturbance travel through the European net, which is this big machine we were talking about before? And that could now also be discussed with the experimental data that we had. So, for example, if in Lisbon something happens, the question is how long do we see that dip in the frequency? How long does it take until you see it in Istanbul? And that you can do as a function of the distance between these places which are connected by this big European grid. And here's the result in these experimental data from the database is if the distance increases, then of course the time also increases that the signal needs to reach this other point. And but it's a quadratic dependence. The time is proportional basically to distance squared, and therefore you see it's a diffusion process. In a diffusion process, you have the square of the displacement goes linear in time, right? So it's a diffusion process through this complicated network of power grid connections, how signals propagate in this system, which you directly can confirm with the data here. Here's another plot that shows once again what I said before, that power grids that are smaller have bigger fluctuations. Epsilon here is plotted. That is the size of the typical fluctuation that you have in your power grid. On the left, you see the power grid of the Faroe Islands. In fact, this work was done while Benjamin was Marie Curie Fellow in London, and we decided he should travel to the Faroe Islands to do some measurements there. So he took his device and went off for 2 weeks to the Faroe Islands and came back with the data. So here you see the results. We urgently needed this data point, of course, for a very small power grid there on the left. And what you see is kind of this fit here that if n, the size of the power grid, which we approximate by the number of people who use that power grid, then you have a 1 over square root of n behavior similar as in statistical physics, where often fluctuations are proportional to square root of the system size. Now, let me come to the point that is on the last part of my talk. I really want to come to the human beings, and they're really interesting because the humans, not only renewable energy, wind fluctuations, weather fluctuations. They introduce fluctuations into the frequency from the production point of view. But the humans, they introduce fluctuations from the consumption point of view. So that is now in a state where you really have also quite interesting data. And I must say, mathematically modeling the humans is much harder than modeling the wind energy or weather or so, because they are basically unpredictable what these guys do. So here you see a typical household today, let's say in Karlsruhe, where people are thinking of the environment. So they go with the bike there and they have a solar panel on the roof. And so there's perhaps also a wind turbine. This is a very good family there in an environmentally friendly house. And then there are their neighbors, and they also use electricity. And the question is, how is that electricity consumption process of the neighbors correlated to that of the first house? And that's a big question mark, because as a mathematician, I would have the simplest model if I could say, oh, the neighbors are statistically independent of the first house, right? They do just their stuff independent of what the house on the left is doing. But that's not the case. People are very correlated in their electricity consumption. For example, imagine they are watching the football right now, or on Saturday, Germany against Denmark. During the break, they all go to the fridge, right, at a particular time, and get their next beer out of the fridge, or run the washing, or do this and that. So you see these peaks in the demand, which are very strongly correlated from household to household. And if millions of people are watching the same football game, you can imagine there are very strong correlations between the electricity consumption between these different households in the next house. So what the mathematician like, the statistical independence, which leads to the central limit theorem, which leads to Gaussian distributions, is violated at fundamental level here. The things aren't simply statistically independent. On the other hand, the things are also not precisely the same. So that would be also easy from a mathematical point of view if everybody did the same at the same time. So there are tiny differences. So these guys have perhaps their solar panel on the roof, whereas the next house doesn't use solar panels, and the third house is not interested in football. You see, then there are tiny differences in their consumption behaviors. So getting the statistics of the electricity consumption, let's say of 10, 20, 30 houses, right, it's a non-trivial problem, and you need data for that. That is precisely what was done in this recent Nature Communication, which I want to spend the last 5 minutes on or so. So in this paper, we then really looked at new data of different households, let's say of 30 houses or so. The blue line that you see here is some German households, that is their electricity consumption over a day, this blue line. The orange line is some Austrian households, some other households. And the purple line is what a lot of industries are still assuming for the daily load profile, is a standard German load profile. So basically, if you don't know the details here, basically the purple line is what the electricity companies assume to happen. And the blue and the orange line is the reality of the electricity consumption on a particular day. You also see there's lots of fluctuations on very small timescales. These are electricity consumption patterns. Every 2 seconds, there are big fluctuations in these data. And you might think, oh, maybe I only need to average the consumption patterns over 15 minutes or so, then I get better agreement with the purple line. But that's not the case that you see here on the right-hand panel. Even if you do the averaging, then the purple line, which is what the typical electricity company would take as a standard load profile in Germany, is not matching the data very well. And this mismatch is pretty expensive for the environment. If you have wrong predictions of what people are consuming per day at a given time, you could save a lot of money if you had better predictions what is going to happen the next day. So therefore, naturally, one should look at these data more carefully and apply sophisticated, let's say, machine learning algorithm or empirical mode decomposition to make predictions for this system. You also see this purple line that I was told, I'm not an engineer, but I was told that these old load profiles are based sometimes on data that were taken in 1970s or so. And in the meantime, a lot of things have changed. So, for example, these households have their solar panel on their roof, and that you see here in the bottom picture. If you see the blue line is a single household, the electricity consumption there over the day in winter and in summer. And the orange line is what this PV, this solar panel on the roof, produces. So you have very big differences between winter and summer. And knowing all this for the individual households would be extremely useful to make better load profiles. So that was the idea of this paper. We can do better than this standard load profile H0 SLP, this purple line. And naturally, you can then do a couple of methods to extract better load profiles. That is here. For example, here on the bottom, you see now the old purple line is now a black line, and the new prediction from a nice algorithm based on some algorithms which I can explain to you if you want, but it's details. You don't really need to know that. You can read it up. So the orange line now is a better load profile that learns from previous data for these individual households. And you see it's not perfect because there are still fluctuations every day. So the next day will look a little bit different. But on average, this orange line is what our algorithm then extracts from the data, and that is much better than the old standard load profile. So the suggestion would be really that one takes this somewhat tedious job rather than having one load profile. You should really look at individual data and construct your perfectly matching load profile for smaller units of electricity consumers. Then you could very carefully estimate how much of the dirty power plants you need to switch on to match the demand. But you also see are these big fluctuations around the average load profile. And you can again look at the statistics of these fluctuations. And as we're coming back to the starting point of this talk, again, you see that the fluctuations around the mean are not Gaussian distributed, but Q-Gaussian distributed. So it's these functions that I showed you in the beginning. And the theory for that can be produced by, again, assuming a superstatistic process where the variance of these fluctuations around the mean is a random variable itself. So everything is then under control, and you can understand both with these algorithms, the mean behavior and the fluctuations around the mean. If that is applied, I think one could really save quite a lot of energy and make more environmental energy resources working at the right time. Yeah. Okay, so basically, I'm at the end of this talk. We have seen, if you look at consumer behavior, it is something very non-Gaussian, something very complex. Part of this non-Gaussianity is due to this so-called superstatistics, which are introduced, that you have processes that are on a small scale Gaussian, but the variance of this Gaussian changes in various time steps. So that produces heavy tails and non-Gaussian behavior. That is one thing. But the other thing is you also have fundamental sort of correlations like the correlated behavior of consumers, which are much more fundamentally non-Gaussian because they're really, you don't have a central limit theorem due to the strong correlations between the people in what they are doing at the same time. And that is, but that makes it interesting for applied mathematicians like me to find best models that fit the data then very well. And yeah, we also, as you can see, these processes that occur sustainable energy generation with a fluctuating variance, we find those also in other time series, for example, of water quality or air pollution statistics. So Benjamin and I just finished yesterday a paper where we applied all that stuff to water quality measurements, which also consists of local Gaussian processes where around the mean the variance is fluctuating on a longer time scale. So many of these mathematical techniques can be applied to other systems as well if you give different meaning to the variables in your equation. Okay, here are some of the references, but I'm at the end of the talk happy to take questions.